Welcome to part 3 of lecture number 5 on finding the inverse to a matrix. In this section I'm going to talk about two rules, Cramer's rule and inverse by Gauss-Jordan, two methods to find an inverse of a matrix, and then I'm going to do a couple of examples. So let's do that. We just got done talking about how to find a determinant. Well, given a determinant, knowing that we know how to find a determinant, we are able to use that information to, there we go, to find the inverse of a matrix using Cramer's rule. So given a matrix M, the determinant is the inverse is equal to 1 divided by the determinant of M times this matrix. So what you do is you take your original matrix, you switch the A and the D, and you negate the C and the B and the C. So here you go. 1 over the determinant, you switch the A and the D, you negate the B and the C. Okay? An example, to find the inverse of A, we find the determinant, which we've done a couple times now. So it's 1 times minus 4, which is minus 4, minus negative 6, which is equal to 2. So the determinant is equal to 2. And then the inverse is 1/2. We switch the A and the D, so minus 4 and 1. And we negate the B and the C, so a 3 and a minus 2. And then we multiply that through by the 1/2, so we end up with minus 2, 3/2, minus 1, and 1/2. That is using Cramer's rule. We'll do a couple of examples, but I'm gonna save those, and we're gonna do all the examples together, both inverse by Gauss-Jordan and inverse by Cramer's rule. So right now we're going to talk a little bit about inverse by Gauss-Jordan. We know how to do Gauss-Jordan. That's the method that we use to solve a linear system of equations when we augment a matrix. We can do the same thing to find the inverse. And the reason we're required to do that is Cramer's rule does not work for larger matrices. The Gauss-Jordan method, on the other hand, works for any size matrix. So the steps are, we take our matrix that we're given and we augment it. We augment it with an identity matrix. So given A, B, C, D, we augment it with an identity matrix. And then we use Gauss-Jordan to get the identity matrix on this side, which is very similar to what we did previously, only we didn't know the term identity matrix then. And what is on the augmented side is your inverse. It's actually pretty cool. There's reasons why it works out this way. We're not going to go into that in this level of a class. This method will work for any non-singular square matrix. There are times when you're not going to get a result, and what happens is if the matrix is singular, in other words, if an inverse does not exist, you're going to get a row of zeros instead of the identity matrix on the left side of the augmented. Let's try a couple of examples. What have I given for examples? We'll just do examples. What I'm asking here is that you find the inverse of these matrices using both Gauss-Jordan and by Cramer's rule. So the first thing we're going to do is we're going to do them using Cramer's rule, and then we're going to do it using Gauss-Jordan. So recall, by Cramer's rule, the inverse, so let's just call this A. We'll call this one M. So A inverse is equal to 1 divided by the determinant of A times, and we switch the A and the D, and we negate the B and the C. Okay? What is the determinant of this? 1 times 9, so 1 minus, so 9. So this is equal to 1 divided by 9 times 9, 0, minus 9, 1. Multiplying that through, we have 1, 0, minus 1, and 1/9. Let's try and do the same thing by Gauss-Jordan. And hopefully I left myself enough space. Perhaps I didn't, but hopefully I did. So we're going to start with this matrix and we're going to augment it. Remember, we augment it with the identity matrix. So I've got 1, 0, 9, 9, 1, 0, 0, 1. Our first pivot is okay. We don't need to do anything to that. I'm going to do a little bit of a shortcut here. I'm going to subtract row 2 from row 1. So this will be row 1 minus row 2. And then I'm going to divide row 2 by 9. So 1 divided by 9, row 2. And that'll give us 0, 1 minus 0, which is still 1. 9 minus 9, which is 0. 1 minus 0, which is 1. 0 minus 1, which is minus 1. 1/9 of row 2, 0, 1, 0, and 1 divided by 9. This part becomes our A inverse. So A inverse equals 1, minus 1, 0, and 1 divided by 9. And that points out that I have just a wee bit of an error right there. It's not supposed to be a negative sign. Don't know why I put one there. So we'll notice that these two A inverses agree with each other. We did one using Gauss-Jordan, and we did the other using Cramer's rule. Let's try it using M. We're going to use the Cramer's rule. So firstly, what is the determinant of this matrix? So the determinant of M is equal to 1 times 4 is minus 4, minus, so we're going to add 2 times 3, which is 6, which is equal to 2. Yes? Okay. What is the inverse of this then? So M inverse is equal to 1 divided by the determinant times, recall that we switch the A and the D, so minus 4 and a 1, and we negate the B and the C, so a 3 and a minus 2, which equals minus 2, 3 halves, minus 1, and 1 half. Okay. Let's try and do this using the Gauss-Jordan method. First step to doing that is augment the matrix. 1, 2, minus 3, minus 4. Augment it with the identity. So I had a little mistake, so we're going to redo that part of it. Anyways, coming back here, we have that our pivot point, we've already made that determination, and then we've got to clear out the column, so we're going to subtract 2 times row 1 from row 2. So minus 2 row 1 plus row 2, which will give us a 0 in the first position. A minus 2 row 1 makes us 6. 6 plus minus 4 is 2. Minus 2 times row 1 is minus 2, plus 0 is minus 2, 0, and then 1. Okay. Now, we're going to keep row 1 the same, and we're going to divide row 2 by 1/2. So 1/2 row 2. And that gives us 1, 0, minus 3, 1, 1, minus 1, 0, and 1/2. We need to clear out everything else in this column. In order to do that, we're going to add 3 times row 2 to row 1. 3 times row 2 plus row 1. And row 2 will stay the same. So that'll give us a 1 and a 0. Those don't change. It'll give us a 0 and a 1. And then 3 times row 2 is minus 3. Minus 3 plus 1 is minus 2. And then this will be a minus 1 yet. And then minus 3 times 3 halves. 3 halves plus 0 is 3 halves. And 1/2. Which gives us, this is m, so m inverse is equal to this part. So that equals minus 2 minus 1, 3 halves, and 1/2. And we'll notice that this and this are the same. So we're doing something correct. So we know that using Cramer's rule and Gauss-Jordan gives us the same result. Let's make it a little bit harder. Let's go to larger inverses, larger matrices. So we cannot use Gauss-Jordan on either one of these. We're required to use Gauss-Jordan on both of these. We can't use Cramer's rule on either because we've got more than a 2 by 2 matrix. So let's start using Gauss-Jordan. There is something you might notice right away. But you might not. But let's say you do. What you can do is from here you can take one step and you can notice that row 3 is 2 times row 1, which means you can leave row 1, leave row 2, and take row 3 minus 2 times row 2. See what that gives us. It gives us 0, 0. I'm sorry, 0, 1. 0, 1. Row 3 is 2 minus 2. Row 2 is 0. And then we have 2, 3. And we'll get another 0. And then we have 5, 7. And another 0. We have a row of zeros when we're trying to do an augmented matrix. Sorry, if we were to do this, we would also augment it first. But noticing this right offhand, we can say, yeah, we're going to get a row of zeros. This tells us that there is no inverse matrix for this value. A has no inverse in this case. Now we're going to try this one. This one is going to have a matrix, and it's going to take a little bit of work to get there. So we were able to find the inverse. No, we weren't able to find the inverse because there is no inverse. We were able to make that determination because we have a row of zeros instead of determining an identity matrix. Let's do the next one. We're going to, again, this is a 3 by 3 matrix. In order to find the inverse, we're going to have to augment it and use Gauss-Jordan. Glancing at it, I don't notice anything that's going to give us a result like we just saw. So let's go ahead and start doing this one. This one might be a little bit more effort, but that's okay. Let's give it a shot. I'm going to augment it. I'm going to kind of shortcut this. Normally I wouldn't do it this way, but we're going to augment this with an identity matrix. And start. First thing I'm going to do is I'm going to switch row 1 and row 3. So let's put row 3. We'll keep row 2 the same, and this would be row 1. So we have 1, 2, 3, 0, 0, 1, 3, 4, 3, 0, 1, 0, and 2, 2, 1, 1, 0, 0. So now we're going to, that's our pivot, and we're going to eliminate the first column, and we're going to do that. Row 1 stays the same. Row 2 is minus 3 row 1 plus row 2. And row 3 is minus 2 row 1 plus row 2. Row 3, sorry. So that gives us 1, 0, 0, 2. Now, minus 3 row 1 is minus 6, plus 4 is minus 2, minus 9 plus 3 is minus 6. Sorry, just continuing this out. 0 plus 0 is 0. 0 plus 1 is 1. And minus 3 plus 0 is minus 3. Okay. The next one is minus 2 times row 1. So that's minus 4 plus 2 is minus 2. Minus 6 plus 1 is minus 5. 0 plus 1 is 1. 0 plus 0 is 0. And then minus 2 plus 0 is minus 2. Okay? Taking a look at this, let's make this a pivot. This is our next pivot point. So we need to multiply this row by 1 over minus 2. Okay? So we divide it by minus 2. We're going to keep row 1 and 3 as the same. And row 3 is the same. So that gives us 1, 0, 0, 2, 1, minus 2, 3, 3, minus 5, 0, 0, 1, 0, minus 1 half, 0, 1, 3 halves, and minus 2. We're going to clear out our pivots. So row 1 becomes row 1 minus 2 times row 2. Row 2 stays the same, and row 3 becomes row 3 plus 2 times row 2. So I've got 1, 0, 0, 0, 1, 0. Remember, we're choosing it so that we zero it out, so I don't necessarily need to spend too much time looking at that. Row 1 times minus 2 times row 2, so 3, so this should be a minus 3. This stays the same. Minus 5 plus 6 is 1. Row 1 minus, that'll be a 0. So 0 plus 1 and 1 minus 3. If you're wondering, so 1 minus 2 times this, which would be minus 3. So that's minus 2. Now we can write all that out, and you certainly can, and I recommend it often. In this case, I'm not going to. Sorry if I was getting too low on that. I apologize if I was getting too low on that. Let me make sure you can see everything. I'm trying to just go down in a single step right now. Sorry about that. Row 2 stays the same. And then row 3 is row 3 plus 2 times row 1. 2 times row 1 is 0. So 1, 0 plus 2 times row 1 is minus 1. So that would be minus 1. And minus 2 minus 3. So that should be a minus. No, I'm saying that wrong. Yes, I'm saying that wrong. So this is a positive, that's why. So minus 2 plus 3 is equal to 1. Okay, we're getting closer. We're almost there. As you'll notice, we already have a pivot. We don't have to do anything else to this value. Yeehaw, that's good. I'm glad to see that. So the next step, and it should be the last step, is to eliminate the other values in this column. So for row 1, that's going to be row 1 plus 3 times row 3. For row 2, that's going to be row 2 minus 3 times row 3. And row 3 is just going to be the same. 1, 0, 0, 0, 1, 0. We know that it'll zero that out. That's why we selected these values. So what do we have left? Row 1 plus 3 times row 3, so 0 plus 3. 1 minus 3 is minus 2. Minus 2 plus 3 is 1. I'm going to write down the values for row 3. Row 2 is row 2 minus 3 times row 1. So 0 minus 3. Minus 1/2 plus 3, which is 5/2. And then 3/2 minus 3, which is minus 3/2. And so our original matrix was B. This is our inverse. So B inverse equals 3 minus 3, 1, minus 2, 5/2, minus 1, 1 minus 3/2, 1. And there we go, ladies and gentlemen. And that Gauss-Jordan elimination can be a little bit exhausting, so there we go.